Now we would like to apply the complex forcing function V sub m e to the j omega t to our circuit and find the current that flows through it. In particular, we'd like to find the real output due to this complex input. Recall that V m e to the j omega t using Euler's identity can be expanded out as shown here to be equal to Vm cos omega t plus j Vm sine omega t. Well, to begin our analysis, we can use KVL around the loop. So we'll apply KVL where we'll take the inductor voltage, VL, plus the resistor voltage, VR, minus the voltage across our source, should add to 0, or we can write VL plus VR minus VME to the j omega t must be equal to 0. We can substitute in the values for the voltage across the inductor and resistor because we know the voltage across the inductor is going to be equal to L times the derivative of our current as a function of time with respect to time plus R times our current as a function of time will be equal to Vm e to the j omega t. Well, this is nothing more than a differential equation where you can see that the function and its derivative will be proportional to e to the j omega t, so we can assume a solution of the form I of t will be simply equal to some magnitude I sub m e to the j omega t plus some unknown phase. Noting that we'll also need the derivative, we might as well take the derivative of the function right away with respect to time. And here you can see that finding a derivative of an exponential function is easy because we just multiply by j omega times the original function, and we're left with j omega im e to the j omega t plus this unknown angle. Now we can substitute these two into the equation, and now we can write j omega L times im e to the j omega t plus the angle plus R times im e to the j omega t plus an angle will be equal to Vm e to the j omega t. Recalling the rules for exponentials, recall e to the a plus b is going to be equal to e to the a times e to the b. We can rewrite our equation as j omega L times im e to the j times the angle e to the j omega t plus R times I sub m e to the j times our angle e to the j omega t will be equal to Vm e to the j omega t. Now at this point you'll notice something very interesting. The e to the j omega t's cancel out of every term. And we have an equation that is strictly in the frequency domain. Notice that there is no time variable in our function. We have j omega L im e to the j phi plus R times im e to the j I is equal to Vm. Here you can see that the only variable in the circuit is the frequency terms omega, and then we'll have the unknown phase. This is known as the frequency domain. Now we can group like terms together, and I can write now R plus j omega L times im e to the j is equal to V sub m, and we can solve for the unknown magnitude and phase of our current e to the j phi will be equal to Vm over R plus j omega L. I can find the magnitude of this function be simply equal to Vm over the square root of R squared plus omega squared L squared. And the angle of our function will be equal to minus the inverse tan of the imaginary part over the real part, or omega L over R. I now know the magnitude and phase of my current, but recall that the actual current includes a time function, and so I can add that back in to say that my current, I, as a function of time, will be equal to Im e to the j. That's my phase angle. Adding in my time function, I can now write that as Im e to the j omega t plus the angle. I can re-express that. I know my magnitude as given up here. I know my phase is given here. So I can write that I of t will be equal to Vm over the square root of r squared plus omega squared L squared all times the cosine of omega t plus my angle, which is given by minus tan to the minus 1 omega L over R, plus j sine of omega t plus my angle, which is minus tan to the minus 1, again, omega L over R. And that completes our function. But we're not actually interested in the complex output because we only really want to find the output due to the real input. And so I can just take the real part and write that the real output, I of t real, will be simply equal to Vm over the square root of r squared plus omega squared L squared times the cosine of our radiant frequency omega t minus the inverse tan of omega L over R. And that becomes the desired output. I have some interesting observations. Perhaps the first one to do is to notice that once we'd found the magnitude and the phase up here, we could have gone directly down to writing the output because that's all we need to know. Omega t hasn't changed one way or the other. The second observation to note is that taking the time derivative, or the integral, of our complex forcing function means that we either multiply or divide by the constant j omega. And the third point to note is that during the analysis, time cancels out of our equations and we enter something known as the frequency domain or the phasor domain. We'd like to explore that further in the following videos.